Sir, in the last question which we did in the previous class,
Yes.
when we check the condition for p greater than equals to -1, the ft dt is convergent for p less than and equal to 0, and for greater than 0 it is divergent. Am I right?
Yeah, so let us start with that particular example today.
Okay, sir.
So first of all, I want to mention that in the last lecture I have stated this condition differently, but now please note that it is as per the integral, as per the LCT for uh, series. So whenever the quotient limit is infinite and the integral GT diverges, we have integral FT diverges. Alright, so this is the change in the PDF file which I have sent after the lecture. This is the example which we were discussing last time. That is e power minus t, t power p dt, whether it is convergent or whether this integral is divergent. So I've written this solution that if we compare this function with 1 upon t square, uh, why we are taking 1 upon t square, because this integral converges, uh, right? 1 upon t power p converges when p is greater than 1. So this integral of gt converges. So I want to compare the given function with gt using limit comparison test. So for that we have to find the limit of the quotient. So limit t tends to infinity of t gt is limit t tends to infinity e power minus t power p by t raised to minus 2, right? So then we go to the next step. Then the power will minus 2 will come in the numerator, it will become plus 2. So now the power is t power t plus 2. So now if we find this limit, so that is the limit of the quotient, and this limit uh, if t tends to infinity, we know that e power t goes to infinity, right? And the same way t tends to infinity, if power of t is positive, then it converges to uh, it also converges to infinity. So now we have two cases, whether the power of t in the numerator is positive or negative. So if the power is negative, then uh, t power negative power and 1 upon e power t, both multiplication will convert to 0, right? If p plus 2 is less than 0, then this power of t is negative, and therefore the limit will become 0. So in that case, we can apply LCT, and since the limit is 0 and the function we are comparing is has an integral which is convergent, the given integral will converge for this case by LCT. All right. So far, any doubt? So this what we have concluded is this integral converges whenever we have the power of t is less than 0. Now the other case is when the power is greater than 0. So p plus 2 is less than 0. That means we have p is less than minus 2. Right. So we have already shown that this series, the given series, converges when p is less than minus 2, because we are getting limit is 0 through LCT. So other case is when p plus 2 is greater than 0, or you can say greater than or equal to 0. So in that case, we will have we will go further, and then we will this particular limit will be of the form infinity by infinity form. So we can apply the L'Hospital's rule, and then we know that when we apply L'Hospital's rule, we differentiate the numerator term and the denominator term. So if you differentiate this numerator term will get p plus 2 times t power p plus 1, right? One power will decrease because we are differentiating. So in this case, now we will get this term instead of the previous term. Previous case we got this term t power p plus 2. Now we got t power p plus 1. So now in this case also we will get the similarly, if p plus 1 is less than 0, then the limit is 0. Otherwise we will go iteratively, right? And then p is less than 0 means this means what? P is less than minus 1. So earlier we got that the series convergent for p less than minus 2. Now once we have differentiated, we got p is convergent for p less than minus 1. So one by one our interval is increasing iteratively. And if we proceed in this way, we will be able to cover the entire real line. Right, so this is basically here we are using Elosthenes rule. So I will share this solution with you. You just go through it. In case you have any doubt, we can discuss after the lecture. So today we want to discuss absolute convergence of the integral. So we know that for the series we studied this convergence. So whenever the series an uh, converges absolutely, that means summation modulus of an converges. Right. So this is called absolute convergence, and whenever we have absolute convergence, we have convergence of the series. So the same way we have this result for the integral, improper integral of first kind. So that I am stating that if our integral a to infinity ft dt converges, then integral itself converges without modulus. So in other words, what we are saying here is that every absolutely integrable function is always integrable. What absolutely integrable or convergent? Improper integral is always convergent. So let us see some example where we can apply this result. So question is that is integral 1 to infinity cos x by x square dx convergent? So here first thing to note is that the function cos x divided by x square is not non-negative for every value of x greater than or equal to 1. Am I right?
Yes, sir.
Yes, sir.
So that is basically what we want to say is that we cannot directly apply the comparison test. So let me just write down that. Note that since the function since the given function cos x by x square may take negative values also, or in fact it is takes negative values. We cannot apply comparison test. So this is just one thing we can note that. So now the question is then how to check whether this integral is convergent or not. So let us see if this integral converges absolutely. So if it converges absolutely, we will conclude that by the this theorem which we stated, and it also converges. So however, so for absolute convergence, we have to take the modulus of the given function. So that is modulus of cos x divided by x square. And the modulus is anyway non-negative for all x in the given interval. So the given function, its modulus is non-negative, and moreover, modulus of x fx, which is cos x divided by x square, that we know that it is less than or equal to 1 upon x square for all value of the domain of the integration. So therefore this function we can dominate by a function which we can say it is a g of x, and the integral of gx is convergent, right? Yes,
Sir, your voice is lagging.
just 1 minute.
No, sir, it's fine.
Yes, sir.
It is
Yes,
fine,
sir.
sir. Hello, am I audible now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So the uh, so where we stop is basically we have compared the given function modulus of fx, which is uh, less than or equal to. Yes, Shobit, you have any question?
No, sir.
Okay.
So my
So
mic is on. Okay, so
no, it's fine. So modulus of fx is modulus cos x by x square, which is less than or equal to 1 upon x square, which is a gx function, and then we know that integral 1 to infinity gx dx is convergent. So therefore, by comparison test, integral of modulus of fx is convergent. So what we are doing here is basically we are not comparing fx with gx. We are actually comparing modulus fx with gx. So therefore, our integral by comparison, our integral with modulus sign is convergent, and that is integral fx dx converges absolutely. And since it converges absolutely, and hence by previous theorem, it also converges. So this is the one way to show that the given series is convergent. So we have shown that this given series integral cos x by x squared dx is absolutely convergent, and once it is absolutely convergent, it is itself convergent. And then we know that this theorem is only in one direction, so we cannot use it for the divergent. All right. So if integral f is divergent, then integral mod f is divergent. But integral mod f is divergent, it is not required that integral f is divergent. So there is one result which we sometimes use for the convergence for this type of series, that is known as Dirichlet test. So Dirichlet test is used when we have an integration of two functions where one of the function monotonically decreasing and it approaches to zero as t approaches to infinity. So we have two functions f and g which are defined on the interval a to infinity to real numbers be such that the first function f is monotonically decreasing and ft converges to zero as t approaches to infinity, and second function g is continuous such that there exists a positive number satisfying the condition on g is that whenever we integrate it from 0 to x, this particular integral we can bound by some fixed number m for every x greater than a. So if g is such a function which is continuous and its integral over the interval 0 to x is bounded by some fixed number for all values of x, and f is monotonically decreasing approaches to 0 as t tends to infinity, then we'll conclude that the integral of the multiplication of these functions ft into gt converges. So this is statement of the Dirichlet test, that if we have two functions f and g from a to infinity to r, and one function monotonically decreasing to zero, another function's integral is bounded, then the multiplication converges. So let us see where we can apply such a result. So one example you can see. So question is that discuss the convergence of integral 1 to infinity sin t divided by t. So this integral we can see that it takes non-negative values, so we cannot directly apply limit comparison test. What about the absolute convergence? If we take absolute convergence, then 1 to infinity mod sin t by t, which we can compare with the integral of 1 upon t dt, right? And then we know that this integral 1 divided by t is diverges, right? So since it is diverged, we cannot apply the limit the comparison test, and we cannot conclude this is absolutely convergent. right? If it is convergent, then we can apply that. So none of the tests so far is working on this example. So let us see whether we can apply the Dirichlet test. So to apply the Dirichlet test, we want to write this function, given function, which is sin t by t, which we want to express as ft into gt. So I hope I'm audible, right?
Yes, sir.
Okay. So basically we want to write this function sin t divided by t, which we want to integrate as a multiplication of two functions where ft is monotonically decreasing and ft converges to 0 as t goes to infinity, and another for another function we want to find m greater than 0 such that the integral. So now here we are integrating the function from 1 to infinity. So we need the integral 1 to x gt dt is bounded for all x greater than equal to 1. So basically this such a function we want. So can you suggest what function will be this one? Fn.
Sir, ft would be 1 by t.
Right, so 1 by t approaches to 0 as t tends to infinity. So that is choice. And the other function, if you take 1 by 2 ft, then dt will be sin
Sin
t.
t.
Right. So let us try that. So it is easy to observe that we'll take ft equal to 1 upon t and gt is equal to sin t. So so first condition is satisfied. So note that ft is equal to 1 upon t converges to 0 as t goes to infinity, and ft is monotonically increasing. Decreasing. Now other condition. For other condition, g should be continuous. So sin t is continuous. So gt is continuous. And now the integral is bounded. That condition we have to verify. So modulus of integral 1 to x gt is integral 1 to x of the function sin t dt. And then we know that the integral of sine function is minus cos t, limit is t is 1 to x. So this is nothing but cos 1 minus cos x. And then we know that we can use triangular inequality, and the cosine function is bounded by 1 modulus of that. So this is less than or equal to 2 for all x greater than or equal to 1. Right. So both the condition of, therefore all the condition of Dirichlet test is where holds. Therefore the integral converges. The given integral converges. So this is the way how we apply the Dirichlet test on a given function. So now Now we have proved that uh, the series absolutely the series converges. So the question is that whether the series converges absolutely or not, right? So it is not necessarily that the given series converges, then it also converges absolutely. So this is one such example. So if you want to check the further the absolute convergence, then we'll see that if you take the modulus of
सर
the
आपकी
series.
वॉइस लैग हो रही है.
Yeah, just one minute. Okay, so maybe it is due to internet. So am I audible now?
Yes, sir.
Okay, so now we are basically checking that the integral is absolutely convergent or not. So for that we are integrating the function using modulus, and then we know that this integral is less than equal to sine squared t divided by t. So because modulus sine t is always less than equal to 1, we get sine square t is less than equal to modulus of sine t. So that we are basically using here. And then we know that sine square t we can write as 1 minus cos 2t by t. So it is equals to 1 minus cos 2 times t divided by 2 times t. And this further we can simplify as 1 upon 2t dt minus cos 2t by 2t dt. So
Can you
finally,
please repeat last 1 minute what you taught?
yeah. So did you understand this Dirichlet test? It integral converges,
Yes, sir.
right? So now we have already checked that the integral converges. The given integral converges. So this example is over, but now we want to check that the integral converges, but it actually absolutely diverges. So we want to check that whether it is absolutely convergent or not. So by definition, we have to integrate with the modulus sign. So to integrate this function sin t by t with the modulus sign, first we will integrate from 1 to x, and then we will take x tends to infinity. So if we take one integration 1 to x modulus of the function, then modulus sin t by t is greater than equal to sin square t divided by t, because the value of sin t is less than equal to 1, right? So since any number less than equal to 1, its square will be less than equal to that number. So that we are using here. So therefore, modulus of sin t is less than equal to sin square t. So that using that this integral is less than equal to the other integral, is greater than equal to the other integral, and then this integral sin square t we will substitute 1 sin square t equal to 1 minus cos t cos 2t by 2. So we'll get this integral. So these two integrals are same, and then we will separate the terms. So we'll get integration of 2t 1 divided by 2t minus integral of cos 2t divided by 2t. So what finally we get is that integral of modulus sin t by t dt is greater than equal to this integral minus this integral, right? And then we will take the limit extends to infinity. So if you take limit extends to infinity, we will get the left side as integral 1 to infinity modulus of sin t by t dt, which is greater than equal to integral 1 to infinity 1 by 2t dt minus integral 1 to infinity cos 2 times t by 2t dt. Right. So now we know that this integral diverges because it is 1 by 2 times the integral of 1 upon t. So by p integral test, since p is 1, the integral of 1 upon t dt is divergent. So we will see whether this integral converges or not. And so can we see that this integral is convergent? Integral cos 2t by 2t dt.
Yes, sir, it is convergent.
Yeah, so which test we will use?
Sir, by Dirichlet.
Dirichlet, right? Because it is non-negative. It is not non-negative term series, and it is also not absolutely convergent. So Dirichlet test we can apply. So note that. So I'm not writing all the steps. Just I'm giving mentioning here. Note that the integral of cos 2t by 2t is convergent by the Dirichlet test. So I'm writing verify. So those who are not convinced may later on verify these. And so now this integral is convergent and this is divergent. So what can we say about this integral?
Divergence.
It is divergent, right? Because if we add this integral with this one, and if this is convergent, then sum of two convergent integral is convergent, and that will enforce this integral is convergent, but that integral we know that it is divergent. So it is kind of contradiction method. You can show that. So therefore the integral of modulus sine t divided by d is divergent. So this says that the given integral is absolutely divergent, right? So the given integral is absolutely divergent. So let me write down here in the next file. So therefore the integral 1 to infinity sine t by t diverges absolutely. So we
सर ये नहीं
observe
कह पाएंगे हम, क्योंकि वो जो मॉड्यूलस वाली होती है उसमें होता है कि कन्वर्ज हो रहा है, मतलब जो मॉड्यूलस वाला है तो ओरिजिनल फंक्शन कन्वर्ज होगा, लेकिन डाइवर्ज हो रहा है तो हम शायद कुछ नहीं कर पाएंगे.
हाँ, so diverge हो रहा है तो we cannot apply that theorem, but that doesn't mean that the function is integral. So basically, since it is divergent, we cannot apply the theorem, and therefore we have to check directly. So directly we have already checked that the integral converges because of the Dirichlet test, right? So this is regarding the Dirichlet test. So now I want to give some remark. So far we are integrating the function from a to infinity.
सर आपने ये क्या लिखा है साइन टी बाई टी डी टी डाइवर्जेस, अभी तो सर हमने बताया था ना ये कन्वर्ज कर रहा है.
हाँ, it converges, but what about the modulus of the integral? So that we are
is
proving,
diverging.
right? So that is divergent, and modulus
So
of the integral diverges. That we will write as the integral diverges absolutely inwards.
ओके अच्छा.
Okay, so now so this example is over. Now so far we have considered type 1 integrals, which are integration a to infinity f to dt, right? So improper integral
सर हम
of the
इसको
form.
शायद कंडीशनली कन्वर्जेंट भी बोलते हैं क्या?
Right, exactly. So the
ओके
series which is which converges but diverges absolutely, it is called the
ओके सर.
conditionally convergent series. Right. So improper integrals of the form minus infinity to a are defined similarly. Correct. So earlier we have considered all the integrals of the form integration a to infinity. So similarly we can define here integral minus infinity to a ft dt, and further we can integrate all the functions from minus infinity to infinity also. So we say that the integral minus infinity to infinity, that means we are integrating the function over whole real line. So this integral converges if integral minus infinity to a ft dt as well as integral integral a to infinity both converges. So if any of this part is not convergent, then the area is not finite. So what I have explained is basically that if we have a function ft and this is the line x equal to a. So if we want to see that whether area under ft over the whole real line is finite area, that means integral is convergent if a to infinity is convergent and minus infinity to a is convergent. So both the areas should be finite, then only the total area will be finite over the whole real line. So this is regarding all the integrals, how we call them convergent or not over the whole real line. The second type integral we will define is improper integral of the second kind. So these particular integrals are basically used for the functions which are not bounded. On unbounded functions, we usually are of this form. So suppose the integral x to b exists for all values of x such that x is between a and b and x not equal to a. So here we are allowing that f to be unbounded on this interval a to b. So we'll see example, but first of all, what is the definition of the integral in this case? So we say that the improper integral converges to a real number m if if this limit, which we define as limit x approaches to a from right side, the integral of x to b if this value is m, so that means the limit exists, limit x tends to a plus of this integral exists, and it is a real number m. Then we say that this integral converges, and otherwise we say it diverges. So let us take one simple example of power of p. So is the integral is the integral 0 to 1 upon t power p dt converges. Actually, I should write that for what values of p.
Sir, can you please scroll down the slide for once?
Just 1 minute. So for which values of p integral converges. Yeah, so this is the definition basically. So we are given the closed interval AB, and we are taking x which is between A and B. So our function is like this fx, and it is given from A to B, and we are taking x in between A and B, and then x approaches to A from right side. So let us try to solve this question. So here we want to integrate 0 to 1 upon t power p dt. So now, for example, if we take p equal to 1, then this function is 1 upon t, and we want to integrate over the interval 0 to 1. So a is 0 and b is 1. So 1 upon t function, is it bounded over the closed interval 0 1?
No, sir.
No,
No,
sir.
sir.
It is not bounded, right? So basically, when we approach to 0, it goes 1 upon t goes to infinity. So it is unbounded at 0. So therefore, this integral is called improper integral because it is not a integral of a continuous bounded function. It is a integration of continuous unbounded integral. So such integral we call second kind integration. So if we to integrate this function, basically we have to find this limit. So since our interval is from 0 to 1, our a is equal to 0 and b equal to 1. So we'll find integration x to 1. So now integration x to 1 upon t power p dt. So if we integrate this once again, there will be two cases. First is p is equal to 1 and p equal to 1 and p is not equal to 1. So p is not equal to 1, this will be t power minus p plus 1 by minus p plus 1. Limit is t is 1 to x, sorry, x to 1. And similarly, in this case, it is log t equal to x to 1. So in both the cases, we get in the above case, we get 1 upon 1 minus p, 1 minus x, 1 minus p power if p is not 1, and it is minus log x if p is 1. So now we will take the limit. So therefore limit, yeah. So finally we'll apply the definition of the integral, improper integral. So this is limit x tends to 0 plus, right? A is 0 here, and then x to 1. So 1 upon t power p dt. So basically we'll find limit in both these cases, p is equal to 1 and p is equal to minus 1. So this will become is p is equal to 1, it is divergent, right? If p is 1, it is divergent. And then p not equal to 1, there are two cases, p is greater than 1, p is less than 1. So if p is less than 1, then what will happen? If p is less than 1, then minus p is greater than minus 1. So 1 minus p is greater than 0, right? So this power is positive. And if this power is positive and x approaches to 0, this is a finite integral. So it will be 1 minus 0 times 1 upon 1 minus p. So it is convergent. So p less than 1, it is convergent. And similarly, you can see that if p is greater than 1, then the power of x will be negative. And if we take x tends to 0, x power negative, x negative power, then it diverges to infinity. So in this case, it is divergent. So therefore, the given integral converges if p is less than 1 and it diverges if p is greater than equal to 1. So basically this integral is nothing but the inverse power of x. We substitute t equal to 1 upon x, then we convert the integral from 0 to 1 of the function to the integral 1 to infinity of x power p dt, and that we know what is the answer of that. Okay, so let me stop the recording here.